In the summer of 2024, the two sides of the Gordie Howe International Bridge met over the Detroit River, connecting the 2,798-foot main span of what is now the longest cable-stayed bridge in North America. This moment had to be carefully engineered, from the tensioning of the cables to the meticulous alignment of each side. Every step was carefully monitored and precisely adjusted. The need for accuracy goes all the way back to the initial surveying of the project, which was a 2-week-long process to make sure that the starting points on each side of the river were precisely placed. In this video, I will walk through the entire process step by step and explain how the hard work of two separate international construction crews was perfectly engineered to come together. Hi, my name is Matt, and if you're new to this channel, I make videos about structural engineering, and today I'm going to be talking about the Gordie Howe Bridge. I'm going to be talking about why we need a bridge here in the first place and why a cable-stay bridge was chosen. Then I'm going to walk through the construction sequence, starting with the pylons, going through the cables, and talking about how the deck segments were added one by one. Then I'm going to show how these two sides ultimately connected in the center and all of the adjustments and alignments that were necessary to ensure that this process ran smoothly. Afterwards, I'm going to talk about some of the weather considerations that were done, such as snow loading and wind tunnel testing. In making this video, I interviewed Grant Hilbers of the Windsor-Detroit Bridge Authority, and I'm going to include pieces of our discussion to help me explain this entire process as I go. As always, I don't expect all my viewers to hold a degree in engineering, so I will be including some concise lessons along the way to help explain the process in as much detail as I can. So, with all of that said, let's get started and talk about why a bridge was needed here to connect Detroit and Windsor in the first place. The bridge spans across the Detroit River here, just south of downtown Detroit, and crosses into Windsor, Canada on the other side. Currently, this international crossing is serviced by the Ambassador Bridge and the Detroit-Windsor Tunnel. The Ambassador Bridge is a privately owned suspension bridge whose owner was not too excited at the prospect of a new bridge. The Detroit-Windsor Tunnel, on the other hand, is owned by the cities of Detroit and Windsor, but does not permit truck traffic, meaning that the Ambassador Bridge has a tolled monopoly on this international crossing. On top of that, both of these connections lack a direct highway connection, so the construction of the Gordie Howe Bridge was advantageous in connecting both Michigan's I-75 to Canada's Herb Gray Parkway. So why a cable-stay bridge? Why not something like a suspension bridge or an arch bridge? This is where economics and climate play a key role in shaping the form of the bridge.
So given the length of the bridge, we had a pretty good idea of what would be the design proposed. We offered in the procurement period for the proponents to either offer up a cable stay or a suspension bridge. Those were the only two options that we included. It's more a performance-based contract that we lay out. These are the things that we're looking for. But it was left to the proponents, but it all comes down to economics.
Part of this performance-based approach likely included some considerations to the icy wintry conditions between Michigan and Detroit. The Detroit River gets ice floats moving downstream during the winter, which posed a threat to the construction crews for any in-water operations. For this condition, a cantilevering approach from each shore would probably be the most efficient, since you can bring in all of the equipment and materials from the ends of the bridge out towards the centers, instead of needing any barges in the water. The construction of a suspension bridge is quite involved and requires the full suspension line to be placed from pylon to pylon before any of the deck is installed. Once the suspension line is in place, the individual hangers must be put in, and then the deck segments can be connected after that. The suspension line must be anchored back into the soil with enough resistance to hold up the entire bridge. These bridges are generally more flexible than the cable-stayed bridges and only find rigidity and stiffness when the full deadload of the deck is applied evenly across the span. Overall, it's a much more complex construction process that may require traversing across the river depending on the construction sequence. One of the things I love about cable-stayed bridges is that its load path is perfectly balanced at any stage of the erection sequence and avoid the need for a super robust anchorage. When a deck segment is put in place, it is lifted at each end by the stay cables. The lateral thrust due to the angle of these cables is then resolved by the deck resisting it in compression. This compression accumulates throughout each preceding deck segment and is either resisted at the abutment or balanced by the compression from the backspan, mirroring the same behavior. The stay cables bring the force of the deck to the top of the pylon, and the pylon holds them up in compression. These cables will either pull the pylon to the side, but this is resisted either by the single backstay cable at the top, or the mirrored stay cables from the backspan help balance out the forces applied to the pylon. The design team with Bridging North America likely took these advantages into consideration in their performance-based approach, and combined with the economics of each option, the cable-stayed design was eventually chosen. The first step in this process was finding the starting position on each side of the river, which required a high degree of accuracy to ensure that they would meet in the middle. This is where the river was once again in the way because they couldn't accurately mark the position of the Canadian pylon by surveying across the width of the river from the Michigan side. The way that surveying works is you have 2 points, point A and point B. In its most rudimentary form, you would take a rope and hold it between each point. With this rope, you adjust the end at point B until the rope is fully level. Then you measure the heights at each end of the rope. The differences in height is then used to find the change in elevation from point A to point B. From this, you can then sum the changes in height as you move from point to point and get an accurate elevation difference across a longer distance. Now, the surveyors for this project were not using ropes. For example, this is a theodolite, which is a modern piece of surveying equipment that allows distances and angles to be easily calculated from point to point both vertically and horizontally. In tandem with the changes in elevation, distances and angles can be used to get coordinates for each measurement, and as you move across a site, the elevation gradient can be accurately plotted.
On this bridge, they were able to start the surveying on the US side, and a survey crew made its way along the US to shore through the existing tunnel, which happened to be under construction during nights in that period of time. So they were able to come through without traffic, and all the way around to the Canadian side. They needed to do that because you can't get accuracy by shooting across the river this length. Spent 2 weeks coming all around, set the monuments on the Canadian side, and after that, there's been continuous survey instrumentation on the bridge that's been fed back into the engineering team. It was not accidental that the closure was so well executed. It was planned years and years before the event actually happened.
So now that the elevations and starting points were aligned on either side, the construction of the pylons could begin. The construction sequence for this involved pouring the footings of the pylons, then post-tensioning the tie grade beam. Then from there, the legs of the pylons were constructed until they connected in the center. Then once they connected, they were able to be constructed vertically up, allowing for the stay cables to attach. A footing was poured at the base of each leg and sat atop 6 drilled shafts that connected all the way down to the bedrock beneath the soil. The footings of each of these legs were connected with a tie beam that was put in place to balance out the lateral thrust from either leg. When each leg is fully loaded with its compressive force, part of that force will want to travel horizontally, so this tie beam restrains that movement and allows for the force to primarily only apply a vertical load on the drilled shafts. The tie beam sits at grade level and is post-tensioned once the concrete is poured. Post-tensioning involves tightening strands within a concrete beam that squeeze the ends of the beam together and pull it into compression. Concrete is naturally weak in tension and derives most of its strength through the rock aggregates bearing against each other, so by supplying compression into the beam before it's subjected to any tension, the beams can perform better and be designed for less steel reinforcement. After these footings were constructed and connected, the pylon legs began to take shape. These extend upwards at a 10-degree angle and meet about 460 feet above the ground. As the straight section of the pylon is constructed, a steel anchor box is compositely connected to the pylon, which is how the steel stay cables connect. This section is hollow, which allows for access and maintenance throughout the lifespan of the bridge. This is crucial in the construction phases as the stays are retensioned multiple times. The anchor boxes extend throughout this vertical section, with the deck segments closest to the pylon connected at its lowest end and the mid-span segments connected towards the top. Once the pylon has an anchor box in place, the construction of the deck can begin.
Generally, you've got 2 approaches for this kind of cable stay bridge. Either a balanced cantilever, where you do all the work from the tower and you just start extending across land and water from each tower at the same time. Or in the case of this bridge, they made a decision to use an unbalanced approach because they had the opportunity to construct on temporary supports on land. So when I say temporary supports, they were some very large temporary supports.
So this unbalanced method involves building out the backspan on temporary supports and starting to connect this to the pylon before the main span is built. Then the materials for the main span deck construction can be brought up onto the existing deck and moved out to the edge of the main span and constructed there.
The real benefit of the construction using this approach was it really minimized the work that was going on in the water. So the Detroit River has ice flows. Some years there's extensive ice, and they wanted to avoid that.
With pieces of the backspan already installed, the main span construction could begin going segment by segment.
The construction over the water is typically referred to as a stick build. So you bring in the steel, the 2-edge girders, floor beams, the redundancy girders, precast concrete panels, and then stitch them together, and then repeat that 25 more times from each direction until you hit the mid-span.
As the deck segments are added, the pylon will start to bend inwards, which will then pull on the backspan, which will help balance out that weight. The cable pretension was adjusted 5 times to help redistribute this force about the pylon. The backspan is connected to 6 permanent piers on the ends, which act as tie-downs that help hold the bridge back in place. Without these tie-downs, the rotational restraint must come from the pylon stiffness itself, but having the backspan held down in place helps stiffen up some of the back cables and allows it to act as backstays that hold the pylon and prevent some of the bending from happening. With all of this in mind, there are a lot of factors that need to be carefully calibrated and perfectly aligned so that they met in the center. So how did they end up doing this to ensure that it connected perfectly? When it comes to aligning the bridge properly, there are 3 dimensions. The ends of each side had to meet vertically at the same elevation. The decks needed to also be transversely aligned so that in plan they would meet, and then longitudinally the decks had to adjust to allow for the right amount of space at the time of construction. The accuracy of the global survey set the paths of the bridge in the right direction in the plan view. Then the elevation of the bridge deck can be controlled by stressing the cables. Put more pretension in and the center of the deck will rise, release some of this tension, and the deck will then get lowered into place.
On the US side, there is the static end. All of the expansion of the bridge is absorbed on the Canadian end, so that's where we have got a large expansion joint. Right before they were ready for the connection, the Canadian bridge segment was released and actually pulled back about a foot. Pulling that back gave room to correct the alignment. And the other thing that was used is, I think you've probably seen the pictures of the cranes on the leading edge. Those cranes were also used as counterbalances. So the cranes were either moved forward or backwards to line up the deck. And then once it was in place, using those jacks, they could pull the Canadian side back to the US side and bolt it.
Once the pieces were aligned, temporary braces were installed, then edge girders were brought in and put into place.
Bolting was also, that activity and the bolting was done in the wee hours of the morning so that you didn't have thermal expansion taking place while you're trying to adjust to all these tolerances. The last thing you want is everything starting to heat up and move, because when you've got a span of this length, it doesn't take a whole lot of expansion to move a few millimeters and get out of tolerance.
With the girder now in place, the 2 sides finally met and the 2 crews celebrated the joining of the bridge. Following this union, the remaining edge girders were placed, followed by the redundancy beams and the concrete panels.
This was one of the most precise, well-executed connections that they can remember of all the bridges they've constructed across the world.
Being a bridge spanning 2 countries, this meant that there were 2 different structural codes the bridge had to satisfy, the AASHTO Bridge Design Code and the CSA Highway Bridge Code, representing the American and the Canadian codes respectively. The bridge loading also had to be carefully chosen based on local considerations, such as how snow would be maintained and plowed. For example, when loading the bridge, it was designed to have a 10 psf snow load applied evenly across the deck. This assumes that the car movement and regular snow plowing will keep a reduced level of snow on these lanes. Then to compensate for this assumption, 82 psf was applied on both of the shoulders, assuming that the snow would then be pushed off to the side with a much higher threshold before removal. The bridge also underwent wind tunnel testing and was designed for a 1 in 10,000 windstorm event. The wind tunnel testing was done by RWDI and involved bringing a small model of the bridge to their wind tunnel.
One of the interesting things that came out of it is the fence on the side of the bridge was actually the one area that we had to change the design on, because at a certain wind spin it hit a harmonic frequency and started to sing.
Other weather conditions include the stay cable sleeves, which are ribbed to prevent large chunks of ice from forming. With the main span structurally finished, the bridge is set to open sometime in 2025. The remaining construction also includes the building of the ports of entry on both the US and the Canadian sides, as well as the connections to the existing highways. If you enjoyed watching this video, make sure to like, comment, and subscribe. I'd also like to thank Grant Hilbers of the Windsor-Detroit Bridge Authority for his time and helping me make this video. If you want more updates or videos about the bridge, you can check out the Gordie Howe International Bridge YouTube or website. All of the media used in this video that wasn't created by me ultimately came courtesy of them, and you can find it all on their website. Thank you again for watching, and I look forward to seeing you in the next video.